All right, the focus of this video is going to be on interpreting odds, risk, and rate ratios, as well as hazard ratios in epidemiology. It's a pretty basic set of skills that are required of all practicing environmental health scientists, as well as persons who are epidemiologists. And it's a very basic skill set that we ought to do and ought to know. So for this example, we're going to use a study from Marine Corps Base Camp Lejeune, where we're going to assess which results are significant in their epidemiological study. Now, Camp Lejeune has been under a lot of scrutiny as it relates to their drinking water and organic solvents in the water. There have been a lot of studies, including this one from Environmental Health, which is a journal that did a study, or the authors did a study in that journal that focuses on male breast cancer in this population of folks stationed at Camp Lejeune. This is a case control study where the cases had male breast cancer and other men had potentially other diseases but not breast cancer, and those folks were either stationed or not stationed at Camp Lejeune. They present crude odds ratios as well as adjusted odds ratios, where the adjusted odds ratios in this paper took into consideration the age of diagnosis of breast cancer, race, and service in the Vietnam War, which was a risk factor. These solvents have been in the drinking waters from the 1950s to the mid-1980s. They still very well may be there, but the drinking water supplies have not been connected for 30 some odd years. A lot of lawyers and lawsuits have been involved. Veterans have had to advocate to get treatment, and it continues to be a bit of a black eye for the Marine Corps and the Navy and other persons that have had folks on that base. But needless to say, in the last decade or so, the U.S. Navy Health Research Center and a lot of other folks have been very active in trying to see which diseases are associated with this water, and many of which are cancer related. So in many of these papers, including this one, we'll get crude and adjusted odds ratios for the disease of interest as it relates to the exposure status or the exposure concentration. So there's a lot of other odds ratios in this paper related to vinyl chloride exposure, trichloroethylene exposure, different doses people may have been exposed to, and so forth. But this is a general layout that you'll see for a lot of epidemiological study papers. We're going to look a little closer. So in this particular study, they had crude and adjusted odds ratios. This is the example of the crude odds ratio. The exposure was ever being at Camp Lejeune or not. So that's a yes or no. We have our cases and our controls. Cases, this is like box A in our little 2x2 table, exposed and disease. These people are exposed to Camp Lejeune water and have breast cancer. Controls, these are people that don't have disease. So we could put them in box D, no disease and no exposure. And you know, you got your odds ratio here and the 95% confidence interval. So what does the OR of 1.45 indicate? What does the 95% confidence interval represent? That's going to be what we're going to focus on going forward in this little quick 15-minute talk. Some example findings in this paper relate to these numbers, and we can punch these numbers into a 2x2 table ourselves and get them. You can use MedCalc to get them by punching in the numbers into that particular website. It will generate a p-value for you. They present a p-value in this paper that they got from logistic regression. This is a pretty similar approach. We'll come back to these numbers here in a little bit. So our focus here is, how do we interpret what odds ratios are telling us? Are things harmful, protective, not significant? And the first number versus this confidence interval, all these things together tell us the whole story. If we just have one of those numbers, we don't have the whole story. So we want to have the whole story, and the whole story here is, for the most part, contained in this 95% confidence interval. This first number, the 1.45, this is our estimate. In this case, it's our odds ratio estimate. But if this was a risk ratio, it could be a risk ratio estimate. So it's our estimate. And this number should always be contained inside the 95% confidence interval. That does not make it significant or not that this falls in that range. It should always be in that range. If it's not in that range, it's a mistake. Somebody messed up. And these other numbers, this 0.87 to 2.44, they are the full range of our confidence of where the true odds ratio lies. So in this case, we are 95% sure that the true odds ratio, the true one, based off of reality rather than just our study, falls between 0.87 and 2.44. This is our estimate based off of our study numbers. This is where we estimate it would be 95 times out of 100. So could the true range, or true odds ratio in fact, be outside of 0.87 and 2.44? Could it be something different than that? This is our 95% confidence interval, and the answer is absolutely yes. This is our 95% confidence interval. With a 95% confidence interval, we have a 5% chance of being wrong. So we could be wrong 5% of the time with these numbers here. So less than 5% of the time, the numbers could be lower. It could be 0.6 or higher. It could be like 3.5. This 5% chance I'm speaking about, this alpha value, is related to our p-value. So in order to do or use this confidence interval, it fits into hypothesis testing. So if we have a hypothesis that Camp Lejeune water is harmful to persons exposed to it for drinking water, we can then make a determination. So can we speculate if Camp Lejeune water is harmful to people or not based upon these numbers? We need a research question. Is exposure to this Camp Lejeune water harmful, protective, not harmful, not protective? So we can find that out using these numbers. We got the confidence interval. It will tell us. Now, when we have odds ratios and risk ratios and rate ratios, when we have these things, numbers greater than 1 are generally referred to as harmful numbers. They suggest a positive association between the exposure and the disease. As you are exposed to Camp Lejeune water, if the odds ratio is above 1, you're more likely to have had breast cancer. And numbers that are below 1, odds ratio estimates and confidence interval values that are below 1 suggest protective. As you are exposed to Camp Lejeune water, you would have a lower likelihood of breast cancer. And then 1.0, if there's nothing going on, that is the number of no association. So we have 3 numbers in our little table. We have our estimate, and then we have our 95% confidence interval. So to get us started off is the 1.45 on the harmful side of the curve of the line or on the protective side of the line. Well, since it's greater than 1, it suggests harmful. The estimate suggests harmful. Suggest harmful. Does not mean harmful, it merely suggests. So 1.45 is greater than 1. It suggests that increased exposure or being exposed is linked to more breast cancer. Therefore, it's harmful. Can we be even more certain than just saying it suggests harmful? We should probably consider using our 95% confidence interval. So our odds ratio with our 95% confidence interval is as follows. You see it? We have numbers that go, we're 95% sure it's between 0.87 and 2.44, and this is our estimate. So are we certain with 95% certainty that it's harmful or not? So our 95% confidence interval is a lower estimate and an upper estimate. They're right there. The lower estimate is 0.87. That's left of number 1. It's protective. And the upper estimate is 2.44. That's harmful. So we have numbers in our confidence interval that range from protective all the way to harmful. And 1 falls in the middle of those numbers. We have conflicting findings. We have a 95% confidence interval that has both harmful numbers and protective. It also includes one saying there's no association, nothing going on. So what do we do? What do we say? So our estimate of 1.45 suggests harmful, but are we 95% sure that it is harmful? No, we can't say that it's harmful. Why can't we say that it's harmful? Well, we have conflicting results. The 95% confidence interval says that we're 95% sure it could be between protective and harmful. If we did say it was harmful, there'd be a 5% chance that we're wrong. It would be a different number than our 95% confidence interval. So having a greater than 5% chance of being wrong is actually having a p-value that would be greater than 5% or greater than 0.05. In fact, our p-value is 0.1582. If we said that that was harmful, if we said the 1.45 odds ratio was harmful, we would have about a 16% chance of being wrong and about an 84% chance of being right. So that's our significance level, p-value of 0.15. So is this p-value deemed significant? Is there a statistically significant difference in the frequency of breast cancer between the exposed and unexposed? Well, with a p-value of 0.1582, that number is greater than 0.05. So we have insufficient evidence to suggest that we have a significant difference using our 95% confidence interval, that there is a significant difference between the frequency of male breast cancer between the exposed and unexposed. Therefore, there is no significant difference between these two groups as it relates to the frequency of breast cancer between the exposed population and the unexposed population. Now, we need to know how to read or estimate the p-values and significance or non-significance by just looking at a paper. Some papers look just like this, right here. There's no p-value presented. Other papers provide it, including this paper. It actually did provide it. I cut it off there just to show you. So, hopefully this has been helpful, and we're going to do some practice odds ratios to help you interpret this. So those are going to be in the next video, and I encourage you to watch the next video for the application of what was just described here, where we're going to be able to look at a bunch of numbers and determine which ones are significant and which ones are not. If you have any questions about either of these two videos, you can email me at jason.marion@eku.edu. So we're going to move on to the next video, and this is the applied interpretation and the actual practice of interpreting odds, risk, rate, and hazard ratios for epidemiology. So tune in for that video, and it should be helpful.